Okay, so we talked about data understanding and data preparation. What are the things that you could apply? Next week, during practical session, we're gonna do data preparation. So let's go to modeling part. So modeling is phase 4 inside CRISP DM. I was happy, no talking. So what we could do during modeling time. Modeling time is simply where you try to map between the input and output in order to find maybe your mathematical equation that represents your data. Let's take example for regression. Let's say if you are applying regression. So what regression is about? This is what we call by modeling. The objective, the goal is to construct a model that forecasts the median house price in California using all other available metrics or features. Here, actually shouldn't be metrics, meaning features. So after all, if we have a regression simply we're trying to find the patterns inside the data, modeling our solution. The solution is simply modeling where we try to actually find the pattern and representing this pattern by equation. So the equation actually will be our model, our solution. So simply y hat means the predicted value, predicted. Predicted y is a function h where the input is x, okay? So h is simply is your mapping, we call it mapping function. Okay, like if you remember the perimeter for a rectangle where we had the rule perimeter equal to width plus 2 height, right? So this function, let's say we call it perimeter for WH, is the way to map between the width and height with the perimeter, which is the value. The rule, because after all, we're looking for rules when we apply data mining, right? So in this case, our equation or our model represented by this value or by this equation for perimeter of rectangle. Here it depends what is the equation, then regression or the modeling, when you run modeling time, then modeling time the algorithm is going to find this equation for you. Okay, so H is simply your model. So you're looking for the mapping function is going to be your model to be learned by the data mining algorithms. So regression analysis is a statistical technique used to model relationship between a target variable and one or more input features. It involves the process of learning a function, this is again the function h, that associate input features denoted as x with the target variable y. Here y is the continuous and scalar value, such as house price prediction. So eventually we are looking to find y hat. Y hat, remember y hat is our predicted value. And what is y? Y is the actual value, Okay, so again, regression is about finding a function h that associate input features with the target variable that you have. So eventually you are looking to find y hat. Okay, now while regression analysis is working, they try to minimize this error. Remember error term? This is the error. So regression has one optimization function, which try to reduce the loss function, the error between y hat and the actual y. Please, if you don't understand, if you have a question, just say, at least I can help you. Okay, so model is simply the function. When we say we trained our model, that means we found a function that actually map between the input and the output, like the case for parameter when we started data mining class, when we said that if we apply regression and then regression is going to reveal the pattern. So the pattern is going to be represented by equation. This equation, we call it a model. The way a model, you model or you map between the input and the output. Now, regression can be linear and can be nonlinear, like correlation. Remember correlation? When we talked about correlation, correlation can be linear. What do we mean by linear? That means you can find a straight line that can model your data, can be your mapping function between the input and output. Okay, regardless whether you have it positive trend or negative trend, it doesn't matter. So still linear as long as you are using straight line. If you are using non-straight line, then we call that we have non-linear relationship. Like this case, we can see there's a pattern like this case. This is non-linear because you have to use a curved line. So we say we have non-linear relationship. How about if you have relationship like this of data? Any patterns? Inside there's no pattern. So even if you calculate regression, regression is going to be very weak. There's no relationship between X and Y, for example. But here we can observe there's a pattern inside the data, but only can be represented by non-straight line, a curved line. So we call nonlinear. So eventually regression, we're looking for the mapping function that map between the input X and output Y. So again, remember, we're looking for mapping function between X and Y. So notice how regression will work. This is if you are going with the optimized version of linear regression, then it will start with many lines until it finds the best line that reduces the error. Okay, I'm not sure it's gonna start again, it's still working. So keep finding the best fitted line. So in other words, we're looking for the best fitted line that reduce the error between the predicted value and actual value. Okay? Because there might be many lines, but we're looking for the best fitted line.
Oh, sorry. Outlier will affect this line.
Yeah, definitely. Outliers can affect, because the error, let's say, not the error, the fitted line. Let's say this is my fitted line, right? How about now if I have outliers here too? The fitted line will change.
Yeah.
And the performance won't be good because these are actually outliers. You should remove them to obtain, this is the best fitted line. Best fitted lines. But now since you have outliers, your model is going to be, yeah, the performance is going to be very low. If you got any data later, which are not outliers, even if they are outliers, let's say later you got here, the performance is going to be very bad for this line because these are outliers. So you should remove them from your data set, unless if they don't have much impact. So if you remove or not, then you notice not much difference. Then you can keep. But definitely they won't be so extreme outliers. Maybe their impact is low. So it depends on the situation. But yes, outliers can actually affect. This is why we need to treat them. If we have them, then we need to treat them and expel them from our data. Now, other algorithms that work for regression case Remember regression, simply when we apply regression, we talked about classification and regression, if you remember. Exactly. Yeah, very good. So when our target variable is continuous. Okay. Now there are many algorithms can support regression. You have linear regression, you have support vector machine, neural network, decision tree, random forest, k nearest neighbor, and others. All of them can work for regression. So let's say for your assignment, you don't need to select one. You can apply all the algorithms. Then maybe among those all, you find 2 or 3 are having potential, good performance. Then you select them. Okay. How about logistic? Logistic regression has the word regression, but actually it doesn't. It's not used for regression. Used for classification. So be careful. If I ask you to give me names of algorithms for for regression, and then you say logistic regression, you lose mark because logistic regression is for classification. Okay, while the rest can be used for classification, can be used for regression, but logistic is used for classification. So again, what we mean by linear regression, where you have straight line, best fit your data. So linear model is a way of describing response variable in terms of linear combination of predictor value. In order to use linear regression, simply you import this class and then you add it inside your pipeline. So next class, practical 4 and 5, we're going to use pipelines. Okay, so later you know how to use them. Simply, this is for the pre-processing part, data preparation, and here is our model, linear regression. Then we fit our model on the data, and finally we can predict. So we have two functions for modeling. For modeling, we have two functions. Function 1, fit. Function 2, predict. For transformation, earlier, transformation, we have fit. 1, 2, transform. We don't have predict. You don't predict for transformation, for pre-processing. You transform your data. While for modeling, you have fit function and you have predict. So linear regression, again, is about finding a linear model that minimizes the sum of squared error. Remember the error, which is the dispute or the difference between y hat and actual y? Because as we said, we may find many lines. Which line we pick? The line that actually gives us the minimum error. Okay? Then minimize the sum of the squared error. So in this case, it's going to be, let's say, this line. Now, regression also has two types, can be simple linear regression, can be multiple linear regression. Simple linear regression where the input, how many variables you have for input features, you have one, single feature. This is where you have single input feature. Multiple linear regression, you have multiple input features. Okay, so this is example of multilinear. So we have more than, this is, let's say, x1, this is x2, this is y, while here we have only x1 and y, simple linear. Okay, so you have one feature. Also, it's called independent feature. You see many terms. We have also, you can say independent and dependent. So remember, we said feature, attribute. So we said we have input feature and output feature, right? Output or target. Another name for input feature, we call it independent variable. while the output or target, we call it dependent. Okay, same name. If we say our dependent variable is house median value, or we say our target variable house median value, same thing. They are dependent. While independent feature, meaning our input feature. Okay, same. So anyway, for simple, we have one independent variable. That means we have one input feature. Let's look into this example. Let's say we are interested to map between education and income. So we collected data for education and we have income on the Y. So this is Y, this is X. After mapping, after finding linear regression, we found that income equal 35.69 plus 2.651 of education. So this will actually mark the income, I think per hour, this one. The income per hour, anyway, it doesn't matter. All right, we need higher income. So we're looking for income per hour. So this would be our mapping function or our model. Or our mapping function. Now what is 2.651? This is, we call it slope. The value, this is theta 1, or we call it slope. Theta 0, or we call it the shift or intercept. Okay, which is in this case 35.69. So what does it mean? The intercept is 35.69, not 5969. Anyway, it doesn't matter. The intercept indicates the value where the line passes through the y-axis. The intercept denotes the expected average income predicted by the model where the education, number of years for education is 0. That means what is the minimum income the person would get regardless of education, right? It's going to be 35.69, the minimum. Now, each 1 year of education, the income will increase on average by 2.65. Right? So this is what regression is all about, is finding patterns inside your data, and then this is how you interpret your results. This is how you interpret your results. I think this was also in the last final exam, similar question on this, to interpret your results. So in this case, when we say theta 0, so if you want to answer, you say theta 0 here represent the minimum average income the person will get regardless of education, or where education is 0. There's no education. Now, theta 1 will represent the average increment on the theta 0 that the person will get for each 1 year. For extra, each 1 year, he's going to have an average income increase by 2.65. That's it. Any question? I think I'll stop here. Yeah, so we were talking about modeling, and we said in modeling is where you try to find solution for your problem. So if you're talking about regression, simply you are looking for a line that best fit your data, right? If we're talking about classification, later we see what modeling means, but at least in regression, we're trying to find the best fitted line that represent the data. How to find the best fitted line? Can we measure how to find the best fitted line? By finding the line that yield the lowest error, right? So if you remember, right? 2, 1. Okay. Puncture. So we find the line that yield the lowest error. So we calculate the error. So let's say we find multiple lines. So the line that yield the lowest error would be our best fitted line. Okay. So we have many lines possible, but the line that yield the lowest error will be our best fitted line. And we said we have two types of regression, simple linear regression or multiple linear regression. Simple linear, simply we have one variable, one input, where multiple linear, you have multiple input. So in your assignment, you have multiple, right? I think simple, I don't know if there's any problem where you need just one input. It's too simple. So when we talk about simple linear, as we said, we have one input and one output. And in this case, we look for theta data, theta value. Okay, so the model is going to find these values. This is why we're doing modeling. I mean, those two values in simple linear will determine your line. This is the equation for a line, right? So once we find theta 0 and theta 1, that's it. So during modeling, actually, we're looking, the algorithm will look for theta 0 and theta 1 that best yield a linear regression or linear model with minimum error. So the quality of your model depends on these, we call them parameters. Those are called parameters. Okay. So we looked into an example. So here we have a data set about education, income, seniority, gender, and party. And we're looking for income here as our target. This is our target, income. And we took education as input. So in this case, we are applying simple linear. If we take more than one input, such as education, seniority, for example, then it becomes multiple regression. So after we fitted the line, after we run regression, we come up with these values for theta. So theta 0 is 35.69 and theta 1 is 2.65. Right? This is our equation that we found. So how to interpret? So if I ask you to interpret your results. So what does it mean, theta 0, according to the context where we are looking to the relationship between education and income? So how we can read or understand the relationship found represented in the line? So what does theta 0 here tells us? 35.69. What does it tell us? Tell us this is the minimum income for a person to get, right? Considering or regardless of his education. Whether he has education or not, this is the minimum income, right? 35.69 USD per hour. Now, what does theta 1? Now, theta 1 tells us theta 1 is 2.651. It tells us for each 1 year, the income will be added or incremented by 2.65, right? So if the person has 1 education year, then top up his income with 2.651. If 2, then just we substitute, multiply by 2, becomes 5 something, and so on and so forth. Okay? So theta 1, which is the slope, describe the predicted change in y for 1 unit difference in x1. So each additional year, in other words, each additional year of education correlate with model predicted changes 2.65, 2 point. This should be 2 point, not comma. Okay, if you like to fix it, this is 2.651 in average income. So this is how you can read it. For each additional year in education, the person will get income, changes in income of value 2.65 in average. Why we're saying in average? Because different people, I mean, eventually the model may have different values, right? Up and down. So we're talking about an average. So for multiple linear, we're looking for more than theta 0 and theta 1. So we're looking for theta 2 since we have x2, theta 3 until theta n. So this is where you have multiple linear regression, where you try to analyze the relation between multiple independent variables. So remember, independent variables means Kaisi, right? Your name Kaisi, correct? Kaizen. Okay, so what do you think? What is independent variable, we said? Or Junlin. What do you think, Suhwan? What we mean by multiple independent variables? Yeah, multiple inputs, very well. So we're looking here for more than one input. We don't have only x1, we have x1, x2, x3, right? So for this example, we're taking education level and seniority level as input. And then income is our y, is output. Okay? So let's say we run regression. Of course, now we're not looking for best fitted line. Now we're looking for best fitted, what we call it, income. So we're looking for best fitted model. Just the word doesn't come to my brain. Okay, so we're looking for the best fitted, what we call it, this one, shape, something. It has a word anyway. I forgot. So the regression plan slopes upward in both education and seniority, with blue point representing employees above plane. Yeah, we call it plane. So we're looking for the plane, the best fitted plane in this case, because we have now 3D, three-dimensional. Okay, so we're looking for the best fitted plane in this case. And now what we notice, let's say our equation becomes like this. So now how to interpret the results. So again, we can say that the minimum average or the minimum income on average is 35.6, regardless of education and seniority. That means if we assume education is 0, seniority is 0, it's not there inside the equation, then this is theta 0. Okay, so if I ask you, you need to interpret like this. So you can say the minimum income is going to be 35.69, considering education and seniority 0. They don't exist. And then for education, you say for each additional year, the income will be incremented by 2.252, right? This is for theta 1. And then theta 2, same thing. But theta 2 seniority, what is the value for seniority? If we check our data set. So that looks like more, yeah, how senior the person, the number of years. So same, we say for each additional year in seniority, the person will get extra 0.739. Okay? Is it clear? So after all, is better you try to understand it to the context, not just look into numbers and say this is regression. But because after all, this gives you insight, right? So this insight has been modeled by an equation. Okay? So we're talking about multiple linear regression. Is it clear? E1? No. Clear? So how to interpret this equation? How to interpret this equation? If I tell you theta 0 here is 35.69. So how to interpret into the context? Zian, right? What do you think? Maybe you help us how to interpret. How to interpret? Sengyi, yeah, what do you think? You say good, I remember some names still. So we can say the income, in this case, the minimum income is 35.69, right? On average, considering education and seniority 0, 0. So if education is 0, seniority is also 0. So we can say the minimum income is 35.69, right? On average. Now, how about education? If we look for education, you need to understand this is maybe real context. You are talking about insights you get from real context, right? So after all, you carry numbers and then you need to interpret these numbers. So you say for each additional year, so now we know the minimum income is 35. For each additional year, the person will earn 2.25 on average per hour, for example. And then for seniority, for each additional year in seniority, also the person will earn 0.739 per hour, right? So it's very good. Use this term for each additional. For each additional year, let's say for education, the person will earn 2.252 income in hour on average. And same for seniority. So now you know it's not just we're looking for equation, but you can interpret the equation. You can understand what these numbers mean. So after all, we're looking for rules, and this is the rule that we found based on the data. This is the rule we found based on the data. Now, if you remember regression, yeah, you're still writing? Okay. Limway? What, Limway? Sorry, what's your name? Oh, Goshen. Yeah, Goshen. I forgot. Goshen. Sorry, your name? Chiho. Okay. So I need to do revision. So I need to call. Is okay, Goshen? Any question? Are you happy? Okay, good. Okay. Now, if you remember, we said regression can be linear and can be non-linear, right? So linear regression is where you're looking for linear, for straight line, or straight plane. Like earlier, also we were looking here for linear because the plane was straight, right? I mean, not curved. Now for non-linear, there are different types. I think here only I mentioned polynomial, but there's different types of nonlinear, and one of them is called polynomial regression. So nonlinear has many types. Okay, it's not only one type, but one example of nonlinear is called polynomial regression. So polynomial regression introduces powers of each features as a new feature, and then training a linear model on this expanded set of features. So meaning, what does it mean? So in polynomial in particular, we are adding powers for our features. So if you look here, we have x, only x, the size. Let's say we're looking to map between the size and the price, the size of apparel, whatever we have, okay, and the price. Now, if we have polynomial, if we have just linear, our equation should be, let's say, y hat equal theta 0 plus theta 1 x, right? Correct? Now, since this is not linear, so if we try to fit here, this will give us many errors indicating underfitting. The model won't be able to find the best fitted line because the data has curved shape, So this will be underfit, will underfit the training data. So what we do, we need to introduce, since the model has the shape of polynomial, then we need to introduce powers to the polynomial. So we take x again, but just we raise it to the power of 2. That's it. I mean, same feature. We don't have here 2 input features. I mean, we have, but they are stem from the same feature. Like education, for example, if we assume education and income has nonlinear in polynomial way, then we say here income equal theta 0 plus theta 1 education plus theta 2 education to the power of 2. Okay, so this is what we mean. We introduce here polynomial term. We introduce polynomial term. And this is one of the regression. If you like, maybe later, I think in another session, we talk about different types of regression. But this is polynomial regression, where you introduce powers to your feature. Okay. Of course, this has negative side if you have many features. Let's say you have 100, and then you introduce powers of 2 to same 100, so you become having 200 features. And how about if you introduce the quadratic power of 3? Then becomes 300 features, right? So if you have quadratic, then theta 3 x to the power of 3. Now here just we took power of 2. Okay, so how about if you introduce, is it possible? Yes, possible. Power of 4, q5 x power of 5. You can. But keep in mind, every time you add more power, you give more power to your model. So eventually, if this is the best fitted model, which is enough for you to have x to the power of 2, enough, right? Here we are able to find the best fitted line by only introducing power of 2. If you keep introducing powers like power of 3, 4, 5, what happens? The models start to overfit. Why? Because your model becomes more powerful. Is able to actually start to cross these lines. You see, maybe eventually if you introduce to the power of 10, maybe your model will look like this. Okay, you see, it becomes like the snake game. So you need to ensure to introduce just enough power. Don't give too much power. Otherwise, your models start to memorize the data and overfit the data. Okay, and the power simply here is give more flexibility to the line to move up and down, to start to cross the data points. Clear? Okay,